Hello and welcome to the webinar presentation, Understanding and Compliance of the Virginia Graham Baker Pool and Spa Safety Act, sponsored by the United States Consumer Product Safety Commission and presented by the Association of Pool and Spa Professionals, Special Initiative, VGBtraining.com. I'd like to introduce our speaker today. Rick English is owner of English Pool Consulting in San Diego. He works as a forensic consultant and litigation specialist involving pool construction, pool service, and pool safety. He has been qualified as an expert witness in California, Arizona, Nevada, Colorado, Washington, and Kansas. He participates in the California Contractor State Licensing Board Industry Expert Program. He is periodically hired by the state of California to investigate consumer complaints. Rick is on the board of directors for the San Diego chapter of the Association of Pool and Spa Professionals, and when time permits, Rick also inspects pools at close of escrow. He is an active affiliate of the California Real Estate Inspectors Association. Rick was president and general manager of Padre Pools, a Southern California pool builder from 1977 to 1998. He has built over 2,000 pools and inspected another 1,500 pools since 1998. Rick holds 2 California contractor's license, California B, and a swimming pool constructor's license. He earned a master's degree in engineering from the University of Arizona and a Bachelor of Science degree in 1967. He is also recognized as a certified building professional from the Association of Pool and Spa Professionals. It's my great pleasure to welcome Rick to speak to our audience on the Virginia Graham Baker Pool and Spa Safety Act.
Hello, as Michael said, my name is Rick English and I am a certified building professional with the Association of Pool and Spa Professionals, and that is the organization that I'm representing today, and we're here courtesy of the Consumer Product Safety Commission to explain how to understand and comply with the Virginia Graham Baker Pool and Spa Safety Act, and we'll get right into it. I'd ask you to please silence your cell phones. I know you guys are getting a lot of calls from your customers looking for inspections, but you can just hold them off for an hour or two. We'll proceed. Here's what you're going to learn today. Why do we have this federal law? What are the hazards and what are their causes? What's required for compliance? And what are the 2 most common compliance mistakes? How can you verify that you're in compliance? And what are some of the alternate compliance methods? We've heard a lot about them. It needs some explanation. How can you audit an existing pool? And this is what you guys are going to be doing when you're out there looking at pools and your client asks you when they're buying the property, do I know that this pool is compliant with the most recent laws? And where can I get more information? Here's how it works. Congress wrote the Pool and Spa rules, and it was signed by President Bush at the end of '07. They gave the authority to the Consumer Product Safety Commission, the authority and the responsibility to enforce the rules. And it doesn't require the state or local government to do anything. It doesn't prevent them from doing something or even making the rules a little bit stricter. But it does preempt state and local authority on minimum drain cover requirements and the need to update public pools and spas. This is a picture of Virginia Graham Baker. Virginia Graham Baker drowned in a spa, and here's the spa she drowned in. It's a conventional gunite spa with a single drain on the bottom, and she was entrapped on the bottom of the spa and drowned. She was the granddaughter of Secretary James Baker, who was the Secretary of State under George H.W. Bush. They were able to use their influence to lobby Congress to get this law passed. And they united with other parents, so it's not just one drowning that caused this thing to happen. There's 3 types of entrapment, and it's important to understand the 3 because we see a lot of solutions out there that address one but not the other 2. The 3 types are, one is caused by flow, and this is the velocity or the speed of the water going through the drain cover, and that typically results in hair entrapment. The second type of entrapment is caused by suction, and this is where the force, the suction force, is great enough to hold somebody down and prevent them from getting out of the pool. Now, the other thing that can happen with suction is evisceration. You'll hear about somebody called Abigail Taylor. You can just Google that name, and you'll hear the horrific story of how she sat on a drain and it pulled her intestines out through her bottom, and she lived for several months, but it finally cost her her life. And the last type, I think, is the one that we miss most often, and that's mechanical entrapment. And this does not even require the pump to be on. And this is where the drain presents an opening that you can stick your hand or finger in and get stuck, like the old Chinese toys we used to play with as kids. We have data from the Consumer Product Safety Commission, and they've collected it from a variety of different sources, and they've done some investigations as to how many of these things actually happen. And here we have the most recent data from 1999 through 2009. There were 94 entrapments, 79 injuries, 38 of them were residential, 21 were public, 10 we don't know. There were 12 fatalities. 7 of those were residential and 4 in public pools. 50% occurred in pools, 33% in spas, 17% in hot tubs. 58% residential, 42% public, 75% of the victims were under age 15. Looking at the hazards, some of the things that cause these injuries and fatalities, we look at broken outlet covers, outlet cover missing, cover removed or disengaged, somebody's caught by an outlet cover, trapped by suction, and unknown causes. 42% were trapped by suction, 41% with a broken, missing, or damaged outlet cover, 17% caught in an outlet cover. So here we have suction, and here we have mechanical entrapment. Let's look at flow first. This is water flowing, and it's going to result in hair entrapment. Suction does not need to be excessive. And here's an example of hair that got caught in a drain cover. The problem is it goes quickly through the drain cover and gets knotted behind the cover. And of course, then you can't get it out without pulling your hair out or cutting the hair. And what's going to cause this is high flow rate going through the drain cover. If you shut off the pump, it doesn't matter once the hair is knotted. You're simply not going to be able to get this person out without cutting their hair. Most people when they think about drain covers don't realize that this is a problem. So the thing we have to know is how quickly is that water flowing through your drain covers? What is the flow rate of your pools? And we're going to spend some time so that you guys can nail that down more accurately. Then there's suction. This is where water flow is blocked and somebody gets trapped, like Virginia Graham Baker, and it results in injury or death. Suction strong enough to hold and trap somebody's back or stomach, arms, upper leg. The problem is suction outlet that can be sealed with or without an outlet cover. And here's an example of a broken outlet cover that presents a hazard, and there's a picture of somebody that was trapped on that cover. This is a picture of my client that I was involved in about 8 years ago. And this is really important for you home inspectors, because home inspectors for years have been telling people, change your drain cover to an anti-vortex drain cover. For some reason or other, we've come to believe that anti-vortex drain covers are safety covers. You can clearly see that this woman was trapped on an anti-vortex drain cover. Anti-vortex means anti-vortex. A vortex is a whirlpool. It's supposed to stop whirlpools from happening. It is not designed for safety. For years we've used those two terms synonymously. We want to stop doing that right now. And I know a lot of you are shaking your heads right now because you've been writing up in your inspection reports, change your drain cover to an anti-vortex drain cover. If nothing else today, you're going to stop doing that. Evisceration, disembowelment can happen in 1/4 of a second at 60 gallons a minute. Injury at the speed of flowing water. The problem is suction outlet with missing or broken cover and buttock seal in a wading pool. Here's an example of a drain mounted on the sidewall, and if there's no other outlet, a person could easily be stuck on that one. And here's a picture of a spa with a single drain, and this is the type that Virginia Graham Baker got stopped on, and we can see that the water goes through there at a tremendous velocity. Lastly, we have mechanical injuries, and again, this is the type that a lot of us don't think of as often because we associate entrapment with pumps, and this does not involve a pump. Openings are large enough for the hand or foot to get stuck. The limb goes in, can't be pulled out. The pump, shut it off, doesn't matter. Small hole finger entrapment. A half-inch hole in a thin drain cover can entrap a child. Entraps like sticking a ring on a finger and you can't get the ring off. The problem, broken or missing drain covers, or the old-fashioned design, drain covers that are not certified. Here's an example of a child that stuck their leg in a return pipe. I don't know whether that's a leg or an arm. And I understand they actually had to jackhammer out the pool wall and take that piece of the concrete, get the concrete out from around the pipe, and then cut the pipe. Fortunately, the child didn't drown because the incident occurred at the water level. Here's an example of a drain cover, and I know when I was building pools, I put lots and lots of these in pools. And that hole right in the center of that drain cover is just perfect for a kid to get their finger through, or an adult. Here is an example of what happens when a drain cover or any other object gets stuck onto a pipe. You can see the force is tremendous. We're playing this back now in slow motion, so you get a feeling for how powerful this force can be. Now, here is an example of a beautiful pool, and this is a pool that the Consumer Product Safety Commission approves of. That's interesting. Here's another pool that they like. Wow. Here's more pools that the Consumer Product Safety Commission thinks are really good in risks of entrapment. Why are these pools promoted by the Consumer Product Safety Commission? The answer is there's no drains. The Consumer Product Safety Commission says that you can eliminate and not just mitigate the drain entrapment hazard in pools and spas by disabling the old drains or building new pools without any drains. Use gutters, overflows, and skimmers to provide water to the pump. The residential pools that I've been designing over the past couple of years have had absolutely no drains, and the circulation systems are just beautiful. The dumbest thing our industry ever did was call that thing on the floor of a pool a drain. In most of the cases, you cannot drain the pool with the drain. It's simply a way of getting water to the pump. We can get water to the pump more effectively by taking it from the top of the pool. Let's face it, all the dirt that gets to the floor of the pool comes through the top. It doesn't generate down on the bottom. So here's another beautiful pool with no drains. So this is one of the 5 alternatives. We're going to discuss all of them. That's being offered by the Consumer Product Safety Commission. So what is covered by the Act? Mandatory requirements for entrapment avoidance in public pools, public drain systems, safety drain covers, residential and commercial, voluntary grants for states for barriers and entrapment avoidance. Drain covers have to comply with ASME 112.19.8-07, and that's 07 or later. Manufactured products have to be tested by a nationally recognized testing laboratory under that same ASME standard, section 3.1.1. Field fabricated outlets, and we're going to talk about those, have to be designed by a registered design professional And we have to look at that same ASME standard, different sections, 2.3.7.7 and 3.1.1. And there's a lot of field fabricated outlets out there. I want you to take a look at this. This is a spa and one of my clients, and it's residential, and I know you guys see a lot of residential spas. And if you look at the floor of the spa, and it's a beautiful spa at a very expensive installation, you can't even see the drains, and that was the idea. They built the drains out of masonry material, covered them with tile, and cut slits in the tile. And these drains are just invisible. And this picture was taken when the spa was drained. There was no water in it, and so it's actually less visible when there is water in it. Now, here's what it looks like underneath those drain covers. So I measured the size of those openings, and I calculated the water velocity going. Now, we're going to notice that there's actually two pipes, which means that there's two pumps working under each of these drains. The total flow rate is going to be over 200 gallons a minute, and I calculated that the water flowing through these drain covers was flowing at a rate of almost 15 feet per second. That is 10 times higher than recommended. So here we have a very expensive, beautiful, gorgeous installation, and this is what we would call an example of a field-built outlet cover that, of course, doesn't meet or come close to any of the standards that we've mentioned. Compliant drain covers have to go through a series of tests, and this has to be done by a registered lab. Either the three that are doing it right now are Underwriters Laboratory, and these tests are spelled out in the standard. A shear load and pull test, a UV weathering before structure test. People don't realize ultraviolet wears these drain covers out, and they do need to be replaced on a regular basis. A fastener test. A lot of people don't realize that the screws that hold down the drain cover are a very important component, and if you switch the screws, the drain cover is no longer compliant. A full head of hair test, and then a ponytail test. Test on the size limit. Compliant drain covers that are field fabricated, that is the kind that an engineer designs for a beautiful residential pool like the one I showed you, or for a commercial pool with a very, very high flow rate, which is where you often have to have field fabricated outlets. They have to be designed for the maximum system flow rate. They have to be UV tested. They have to have some specifications, body entrapment calculations, structural analysis, and a finger test. This has to be proven before we can say that that drain, and that has to be certified by a professional engineer before we say that that drain is compliant. These are the compliant drain covers, and just to give you an example of some of the things that you should be looking for, there will be labels on the cover that clearly say that it's VGB compatible, and you're going to see several different examples. Manufacturers have a little bit of latitude. This just says VGB 2008, patent pending. This next one will be slightly different. It says floor only, life 7 years. They have to have a lifespan on them. Some will say they're listed for floor only. Some will say they're listed for floor and wall. But there will be different flow rates for floor and wall. Obviously, the flow characteristics are different if it's vertical. So here it says wall 112, floor 255 gallons per minute, life 7 years. This is the type of information you want to be looking for. These are all the different covers, and you'll note that we have covers here. These older covers here are not VGB compliant. The newer ones here are VGB compliant. The drain cover rating must be higher than the maximum system flow. Choose a drain cover based on 100% flow through the drain system, assuming that there are no skimmers or overflow systems operating. Each cover requires a flow rating equal to or greater than the maximum system flow, unless there are 3 or more drain covers piped together without valves. You have to assume that one cover is blocked. So we have dual drains, and we assume that one of them is blocked and the other drain cover can handle the whole flow. Let's take some examples. We'll assume that we have a maximum system flow of 140 gallons a minute. We have a VGB compliant drain cover, and the printed right on it is 100 gallons a minute is the maximum that can go through that drain cover. We have a dual drain system, and we have 2 drain covers rated at 100 gallons a minute. That's 200 gallons a minute, right? Wrong. 100 plus, you don't add. You have to assume that one of them is blocked. So we only have a system that's rated for 100 gallons a minute. Now let's say we have a 3-drain system. And remember, these drains have to be balanced, and it's a little tricky to balance 3 drains. So we have 100 plus 100 plus 100. We assume that one of the 3 drains is blocked, and we do have a 200 gallon a minute system, and that system is greater than 140 gallons a minute, so this would be a compliant system. Dual drain system. Why each drain should be rated for the full flow? Here we're looking at the dual drain video, and we see the water flowing through the system. The block comes down, covers the one drain, the other drain has to handle the full flow. So let's look at that again. We have both drains working nice, they're balanced, and the block comes down and interrupts the flow on one of them. The other drain handles the full load, and we can release the blockage that comes down. Now, we're going to talk about plumbing. Here is a plumbing plan done by an engineer for a pool and spa. And the reason we're looking at this is we're going to show you how things change in the field. Oftentimes, using that same plumbing plan, and let's assume that they follow it and they try to follow it almost to scale, you'll notice that over here, this pipe had to go across. So the plumber had to install a 90 245s in order for this to go into the pool. If we look back on that plumbing diagram, we'll see that that pipe goes straight across, but obviously it can't go right across the other pipes. So what we're going to find we need to learn how to handle is a concept called total dynamic head, which is the sum of all the resistances that the pump has to overcome. And we're going to see how that can be measured on a plan and how it can be measured in the field. Things change in the field a little bit. This is a picture that I took of a pool that I was inspecting up in northern Los Angeles, and I don't think any engineer ever drew this plan. Here's another beautiful plumbing design designed by an engineer, and see how they use these nice little loops to show how pipes go over. Well, this loop could be done with 445s, it could be done with 490s. Who knows how it's actually going to get implemented in the field. They don't specify that kind of detail. And of course then you get systems where in order to make things work, the plumber has to be really creative. So if we know the total dynamic head, we can determine the flow. Calculations have to include all the resistances in the system, piping fittings, valves, other system components. The problem is that what we call calculations are really estimations of the system resistances, and they're always higher. Let me explain why they're always higher. When we get a plan approved for a public pool, the health officials that approve that plan want to make sure that the system is going to turn over in a certain amount of time. Used to be 8 hours. A lot of jurisdictions are using 6 hours now. They want to make sure that 100% of that pool's volume goes through the system in that amount of time. So they would rather underestimate than overestimate. They'd rather, if it goes through a little bit faster, they're happier. If it goes through slower, they're not happy. So they want to eliminate that chance of it going through slower. And everybody knows that. So our whole system is rigged to underestimate the flow because we want to make sure that that filter system is working. And that's great from the standpoint of circulation and cleaning and chlorination and sanitizing and killing of bad things in the pool, keeping that pool sparkling clean. That's great. But it's not great for designing drains. And so we're going to go back and learn how to make the necessary corrections. So here's how pool hydraulics works. We determine the pool volume in gallons. That's another class. We're not going to do that today. Calculate the desired flow rate based on a turnover time, usually 6 hours. Then determine the resistance in the system. We're going to do this on paper. And then select a pump based on the desired flow rate and the resistance in the system, which we call total dynamic head, by using a pump head curve. Every manufacturer is required to provide a pump head curve that shows how their pump performs under varying total dynamic head conditions. So let's take an example, a 25,000 gallon pool. First, we're going to determine the flow rate in gallons per minute. We want to turn over in 6 hours. That's 360 minutes. Very simple. We divide 25,000 by 360, we get 69.4. We're going to round that to 70 gallons a minute. Once again, you can see my little bias here. I would never round that down to 69 because I want to be 100% sure that I'm going to turn over that pool in at least 6 hours. Here's how TDH is estimated. We're going to add up, we're going to take this plumbing diagram and we're going to add up all these resistances. Again, we're going to assume that the skimmer is not part of the system. So we've got all these distances measured out. We need 70 gallons a minute. We're going to measure the pipe, count the fittings and valves, and the equipment, return, and drain fittings. And we're going to use manufacturer's data for all of those different components. And all this information is readily available. So here is how friction loss works in Schedule 40 pipe, which is what we use for pools. And you can see from this diagram that we first look at the pipe diameter, 2-inch pipe diameter, 2.5-inch, 3-inch, all these different pipes, and down here we get the bigger pipes, 5, 6, 8-inch pipes. So we're looking at 70 gallons a minute. We are looking at 2-inch pipe. So we connect the dots and we see that 100 feet of 2-inch pipe, when water is flowing at 70 gallons a minute, will produce 7.76 feet of head. So let's get that straight again. 100 feet of pipe, when water is flowing at 70 gallons a minute, that's 2-inch pipe, will produce 7.76 feet of head. So what we're going to do then is convert everything else into equivalent lengths of pipe. And again, we get this information from the manufacturer. So for example, for 2-inch pipe, we have a 90-degree elbow. Instead of saying, hey, we've got a 90-degree elbow, for purposes of calculation, we're going to say, no, we got 5.7 feet of pipe. And if we have a T, where water's going through the T, in a normal fashion, water goes in and branches out in 2 different directions, we're going to say, oh, we don't have a T there, we have 4 feet of pipe. And again, just for calculation purposes. And a T with a branch, we're going to assume that that's 12 feet of pipe. So now we can use our friction loss for return fittings. And again, we're going to have 1-inch return fittings that are plugged on the end of these, the end of the return pipes that go into the pool. And we only count 1. And again, the manufacturer tells us that a 1-inch return fitting flowing at 25 gallons a minute, remember we've got 3 of them, is going to give us the equivalent of 65 or 1.6 feet of head. So let's look at our diagram again. On the suction side, we have 104 feet of 2-inch pipe. Looking at our diagram again, on the suction side, we have 9 90s that are equivalent to 5.7 feet of pipe, so that gives us 51 feet of pipe and 104 feet. We have 2 T's going to be equal to 12 feet each. That's 24 feet. We have 1 3-way valve that's equal to 12 feet. We have 2 drains that are equal to 2 feet each. That's a total of 4 feet. So on the suction side, we have the equivalent of 195 feet of pipe. So now we just multiply that by 7.76 feet, and we get 15 feet of head on the suction side. Now on the return side, we do the same thing. We have 182 feet of pipe. We have 2 1090s at 5.7 each. We have 2 T's. We have a total equivalent pipe of 247, and that gives us, at converting that to feet of head, 19.2 feet of head. So we have 15 on the suction side, 19 on the discharge side. Suction side lost 15.3, return side lost 19.2. Our loss to the filter, which we get from the manufacturer, is 12 feet of head. Our chlorinator loss, that's this guy over here, is 2 feet of head. We get that information from the manufacturer. Return fitting loss, remember we only count one as 1.6. So we get a total loss of 50 feet of head. That's all the calculations we need to do on this particular drawing. Now, if we want to measure in the field, on the same system, we don't count any pipes, we don't count any fittings, we don't measure pipe diameters, we don't look at anything except 2 gauges. We install 1 gauge on the front of the pump, which is the suction side, and we install 1 gauge on the volute, which is the pressure side, and we measure one in inches of mercury and another in pounds per square inch. And it's crazy, our system is, our pressure gauges read in pounds per square inch, our vacuum gauges read in inches of mercury, so we need to go through a conversion, and the conversion factors are right down here. Can multiply pounds per square inch times 2.31, we get 32.34 feet of head, and inches of mercury by 1.13, we get 2.26, so we have 34.6 feet of head. On the same system that we just measured 50 feet of head in the calculation stage. So here we have 35 feet of head that we got the result from doing the measurements in the field. And this is so important now for drain cover fittings. We're going to look at a pump curve, and this is how pumps work. Pumps, their performance will change based on the feet of head that they're facing. So for example, a 1.5 horsepower pump will not move, will completely come to a stop at 80 feet ahead. A 1 horsepower pump will stop at around 76, and a 3/4 horse pump will stop at 60. Going up to the other end, let's say 50 feet of head at 50 gallons a minute, we would get that at 40 feet of head on the 3/4 horse pump. We would get that at 60 feet ahead on the 1 horsepower pump, and we would get that same flow rate at 65 feet ahead on the 1.5 pump. So you can see that we can actually get a lot of different flow rates out of pumps as long as we can control the total dynamic head. So we measured 50 feet in the laboratory, in the field, in the office, doing our calculations, the one that the health inspector is going to approve. So we measure across, we need 70 gallons a minute. We better use that 1.5 horsepower pump. It's actually going to give us about 74 gallons a minute. We better use that 1.5 horsepower pump. But then we went out and did our field measurements, and we got 35 feet ahead. Selected 1.5 horsepower pump. It's not going to give us 70 gallons a minute, 74 gallons a minute. It's going to give us 92 gallons a minute. So we predicted in the office that we would be getting 74 gallons a minute, but in reality we're going to be getting 92 gallons a minute. That's when I said the system is rigged to always underestimate flow rate. So this pool is going to be a lot cleaner than the health inspector and the builder think, because it's going to turn over faster. But the penalty we have for underestimating flow rate is that we might undersize the drain covers. 92 gallons a minute actual versus 72 gallons a minute predicted. If you know TDH, you have to measure. That will give you flow rate. Now, a lot of people will say, but hey, I've got a flow meter on my pool, and the flow meter tells me what the flow rate is. Well, let me caution you that flow meters are not very accurate. First of all, very few times do I see them installed properly. Secondly, a flow meter can't measure flow. It can only measure, it can't measure gallons per minute, which is volume. It can only measure velocity. And it's going to measure it based on the inside diameter. Well, let me tell you that inside diameters can vary in pools, in pipes. So if your inside diameter is inaccurate, your flow rate is going to read differently. Now, if you look at, and I ask you to go out and look at pools that you've inspected recently and look at that flow meter. There's supposed to be 10 inches of pipe installed ahead of the 10 times the pipe diameter installed ahead of the flow meter. So if you have a 2-inch pipe, that's 20 inches of pipe, perfectly horizontal, going ahead of that flow meter. And then 4 pipe diameters, or 8 inches of pipe in the case of a 2-inch, after the flow meter. If you don't have those pipe diameters, if there's a 90 or a T closer to the flow meter, then what we have in the water is turbulence, and the flow meter readings are going to be inaccurate. Health officials use flow meters, and they're okay for everyday use, for making sure that your filter's not clogged and that sort of thing. But as far as accurately determining the velocity of water going through your drain covers, we don't recommend that you rely on them. Now, there are some real high-end flow meters that you can rely on. Flow meters have to be installed properly. Now, if you want, a lot of you, when you were looking at the testing that I did in installing those 2 gauges and making those conversions, you thought, that's more math than I want to do. I'm just not that comfortable doing math. So for those of you that aren't comfortable doing math, we have a little video here that will show you how to use something called the AquaCal.
Okay, what we're going to do here is we have a differential pressure gauge, and this one reads directly in feet of water. So we're going to connect the low pressure side to the suction side drain plug. We're going to connect the high pressure to the pressure side drain plug, and between the two we'll get a direct TDH reading. So let's do that. Now we got our pump up and running, and what we're going to do is just bleed by opening this T. We make sure all the air leaves the system. And now what we have is a total dynamic head for this pool of 56 feet of head.
Okay, so that's Steve Barnes showing you how to use the AquaCal test kit. I just carry a vacuum gauge and a pressure gauge, and I don't find the math that difficult. But if you want to do a lot of these tests and you want to do it very simple to get a direct reading of feet of head, you can purchase the AquaCal test kit. It's available at the APSP website. If you're a member of APSP, it's only $495. Measuring TDH. Now you can go to a pump curve with an accurate measurement of TDH and determine the actual system flow. Select the correct pump. And if you haven't selected the correct pump and then you're dealing with an existing pump, you can select the covers with a flow rating equal to or higher than the system flow. Measurement is the only way to accurately determine the total dynamic head, and it works on any pool, new or existing. The Virginia Graham-Baker Act says for public pools and spas, they are required to have VGB certified suction outlet covers. The cover consists of a fastening system, a cover, a sump, and the correct flow rating for the pumps. It requires a system update for single drain configurations and multiple drain systems less than 3 feet center to center or on separate planes. Here we're looking at some of the other alternative solutions, for example, safety vacuum release switches, suction limiting vent systems, gravity drainage systems, and automatic pump shutoff systems. Drain disablement. Remember we said earlier drains are not required in pools for circulation purposes or some other equally effective systems. Here's an example of pump shutoff or safety vacuum release switches. We tend to lump the two together. They depend on your pipe sizing, your flow rate, the ability to entrapments. But remember we said that shutting off the pump will not prevent hair entrapment. So we still have to have the correct flow rates. They're called safety vacuum release switches. We have vacuum limiting vent systems and gravity drainage systems, which we'll explain in detail in a few minutes. And here are some examples of automatic pump shutoff systems. This one here, the vac alert, is actually not a pump shutoff system. It simply opens up and lets air in the system. But we tend to lump those into the same category, safety vacuum release switches. Here we have a suction limiting vent system. And what happens with a suction limiting vent system is that if the drain gets blocked, covered over here, then the pump is going to pull the water down to this point, and it's going to release the vacuum on the system, and it'll release the person or item that's trapped on the drain cover. Once again, this will not prevent hair entrapment, so we still have to have the correct velocity going through the drain covers that are on top of this. Here we have a gravity system, which is similar to the last one we just saw. The gravity system, the water is actually being pulled out of a tank. And this is very common in older public pools. And when the drain gets blocked, the tank gets drained down and it releases the pressure on the system. Very similar to the last system that we looked at. And these are the safety vacuum release switches. If you're going to disable the drain, you don't just want to cut off the drain, because remember we talked about mechanical entrapment where people can get their hands stuck or their body stuck on the drain cover. You actually want to take out the drain and cover it with plaster, get rid of it completely, and just eliminate the cover so the cover no longer exists. You can also take a single drain and convert it to compliant drains that are properly balanced. Be careful that some people were out converting drains and they were putting the drains in series. That is, instead of having a T in the middle like we see here, they would have the pipe would come into one and then branch out to the other, and there would be nothing in between the two. Obviously this one's going to have a lot more flow going through it than this one. They're not balanced. They must be balanced. We can permanently disable the drain, convert the single drain to a dual drain. We can also convert the drain to a return. And we want to make sure that the water going through there is going no faster than 6 feet per second. We can also convert blockable single drain systems into unblockable single drain systems. And everything may not be as it seems. Here we have a video taken at a hotel. I believe it was in Chicago. And this hotel spent money to get in compliance with Virginia Graham Baker. And as you can see, there are two very nice, very well separated compliant drain covers, very similar to the ones I showed you earlier on the floor of the pool. Now let's go over to the spa and have a look at the spa. And what did they do here? You can see that they updated the drain covers by splitting the drains. You can see where they repaired the plaster and they put two compliant drain covers on the floor of the spa. Very nice. There's another drain on the sidewall. Remember that picture that I showed you earlier of a lady that was trapped on an anti-vortex drain cover and had the marks on her back? This is exactly the type of thing that got her. So we want to make sure. Now, I'm not saying that that particular drain is not compliant, but we want to make sure when we review something that we look at all the pumps. A lot of systems will have extra pumps on them for waterfalls, water features, slides, that sort of thing. And if it's a drain, it needs to be compliant. So here we're taking a second look at the spa. And here we can see that drain on the side. And it distracts us from looking at the very nice job they did on the floor of the spa. Okay. And the point we want to make here that it's not just a simple plastic swap. Suction fittings include the cover, the frame, the sump, the hardware, and the fastening system. Existing frames, sumps, and fasteners must meet the standards, so you can't even change the screws that you use to hold down these drains. Field-built sumps, cover and frame not connected to a pipe, must comply with cover manufacturer's instructions. When the manufacturer doesn't give instructions, then we have to follow the details that are given in the ASME standard. Here's an example of a sump, and we measure from the ring around the frame around the drain cover down to the pipe, not the bottom of the pipe like it shows here, but to the top of the pipe, and that has to meet either the manufacturer's instructions. Some manufacturers will even say you don't have to have a sump. As long as it's been tested by one of those three labs, we can follow that instruction. Here are what field-built sumps would look like if the manufacturer does not give instructions. The pipe that enters the field-built sump has to be down, the entry point has to be down 1.5 pipe diameters, whether it comes in this way, or this way. And all other parts of the drain have to be down 1 pipe diameter. So if we have a 2-inch pipe, then it has to be down 3.5 inches. 3-inch pipe has to be down 4.5 inches. So we have to, a 2-inch pipe would have to be down 3 inches. So we have to go by this if there are no instructions. Most of the drain covers in the part of the world that I come from, which is Southern California, are field built. Most of them. Every pool that I ever built had a field built sump, and I stopped building pools as a contractor in 1998. Every one of them had a field built sump. And I've been inspecting pools as a member of the Home Inspectors Association for the past 13 years. And I drain the spas in every one of those pools and inspect the drains, and every one of them that I've inspected has a field-built sump. So this is a common condition that we have in Southern California, and I'll tell you right now that in all the pools that I've inspected, I haven't found more than a half a dozen that actually comply with this standard. Why sumps matter? Sumps matter because the flow going through every one of these little openings in the drain cover has to be going at the same rate. So even if the pipe underneath the cover is centered, it's going to, if it's not down deep enough, the flow is not going to be evenly dispersed over that cover. It's going to be uneven. We're going to have more flow at the center than we are at the outside, or more flow at one side than at the outside. So we want to be very careful about the sumps, because we can spend all this money changing out the drain covers, and if the sumps are giving us uneven flow, it's defeated our whole purpose. So in this video, we had an 8-inch suction pipe, 3 inches from the cover, and low flow around the edges, and there's a screw missing too. So installing a new compliant cover will not make this drain safe or compliant. This is a good example of why you can't swap plastic. Remember, the drain includes the cover, grate, sump, fasteners, and other components. Now, there's also something called an unblockable drain. This is a suction outlet. Again, all the components, sump, body, cover, grate, hardware, such that its perforated opening cannot be shadowed by an area of the 18 by 23 body entrapment element. And this is the 18 by 23 body entrapment element that's been defined in the ASME standard. And here is an example in real life of what one looks like, and this is what is used in the testing laboratories to see if the drain cover is unblockable. And as you can see here, when they put this on this drain cover, there's still open area for the water to flow around. And so this alternative of an unblockable drain, there's an example of a large drain, and that can't block the 18 by 23 area. If it's larger than 18 by 23, it may be placed over a smaller sump to replace a smaller cover. So we've seen quite a few of these on big systems. Here's an example of that same 18 by 23 that mounted on a wall. And you can see that here he's holding up a flat drain. One of the issues with this standard is we don't want flat drains anymore. They're just a lot less likely to entrap if there's a slight dome. So here we have a replacement drain that would fit in that same fitting, but it's domed and less likely to cause entrapment. Here we have an old drain cover, flat drain cover, and in addition to being perfectly flat, you can get your finger stuck right through this cover. This is the cover that I put on my own pool drains in 1981 when I built the pool. Trust me, it's not there any longer. Here's another flat cover that would be unacceptable because of its flatness. Here's an example of a cover that goes on an equalizer pipe under a skimmer. It's also domed. Equalizer pipes, by the way, under a skimmer are not required. Unless your health official insists on them, I would not put in equalizer pipes under skimmers, and that way you don't need to worry about the cover. Here is a large custom design unblockable drain. With the hardware. and there's the element placed on top of it. Here's a channel drain, and channel drains are also acceptable as considered unblockable drains because of their length. And again, by placing this element on the channel drain, we see that it can't block it. Here's another custom-built drain cover. This would have been designed by an engineer for a particular job. And here's the element on top of it showing that it's unblockable. Is your existing pool safe? Audit the pool to determine if it's compliant with the Act. You can use an ANSI APSP 7, and that's the name of the standard, the ANSI APSP 7, Appendix B field checklist for identifying suction entrapment hazards. It's a flow chart, and it works beautifully. You start at a certain point, it asks you questions, and depending on the answer, these are yes-no questions. Yes, you follow this branch. No, you follow this branch. This is a single drain or multiple drains. Single drain, you follow this branch. Multiple drains, you follow this branch. It makes it very easy. Here we have a video showing a little more detail how this system, how that sheet works. You start at a certain point, you ask the question, what's the maximum flow rate of the pumps? What's the maximum combined GPM in a multi-pump system? And then we move on to the next branch of the audit sheet, asking a series of questions that reference back to the standard to help you make a decision about what to do next, what action you can take. Detailed question, is the cover undamaged? Is it adequately secured? Is the sump a fabricated sump? Is the field sump compatible? All these questions you can ask and go through this checklist. You can then give this to your client, and for you home inspectors, this would be a real blessing because everything is right there. And for many of you home inspectors, what you're probably going to decide to do is to refer this out to a specialist who this is what they do. The back side of the checklist shows how to do that total dynamic head test, and it even has the conversion factors there. It shows you how to do gravity flow calculations if you want to get that fancy. And you can fill out this information, sign this sheet, and give it to your client, and they'll know exactly where they stand. The other thing it'll do is it'll give you a record of the audit that you did, and if you get called back onto this site, let's say after there's an entrapment incident, you would have a copy of this. You can buy these in packets of 25 at the apsp.org website. It's $29 for 25 sheets if you're a member of APSP, and $49 if you're not a member. For more information on drains and drain safety and other general swimming information, the website has been designed by the Consumer Product Safety Commission is poolsafely.gov. Poolsafely.gov has lots of information to help generate awareness about these different types of entrapment errors, education for people like yourself, home inspectors, anybody else that's interested, and it's outreach to get the information out to as many people as possible. We invite you to go to the website with any other questions and join the team. Meanwhile, if you have any questions for me now, I'll be happy to entertain them.
So, Rick, when we're discussing VGB, can you give us an idea of what's code versus what is industry standard?
Code is something that's actually written down in a building code and has been adopted by your local enforcement agency. For example, in the city of Los Angeles or city of San Diego, they will have adopted a code. They may be working on a code that's several years old. In fact, that's typically is the case. Industry standard is something that's developed usually formally by an organization like APSP, Association of Pool and Spa Professionals, American National Standards Institute. There's a variety of the International Plumbing Manufacturers Association. They develop industry standards, and they're not enforceable by a building inspector, but they are what the industry expects people to do. So when we get into litigation or lawsuits, the industry standards always come up, and the attorneys use a term for it, the standard of care. Is this what the industry expects you to do? So it pays an inspector to pay attention to both industry standards and to codes. And I know we oftentimes get in a position where people are saying, do I have to do this? It's not code. And your best response to that is to say, it's not code, but it is industry standard, so I recommend that you comply with the industry standard.
Great, thank you. Great answer, Rick, by the way. So, Rick, as an experienced pool inspector, how do you inspect a pool for VGB compliance? And then maybe you could explain for those of us who aren't as familiar with pool inspections, how should we be inspecting a pool for VGB compliance?
Well, you saw the presentation, and in order to inspect for VGB compliance, we have to find the velocity of the water going through the system, the gallons per minute, and we do that by checking TDH. And I carry the proper tools with me to check for TDH. Then I have to literally remove the drain covers and measure to see if they're properly spaced. I'll measure to see if the sumps are the proper depths and make sure that the cover is certified. And fortunately, we have that compliance sheet that is available from APSP that you can just fill out, and I use it. I find it very handy for inspecting pools for VGB compliance. Those of you that are home inspectors, I would recommend that this might be a little bit more than you would want to incorporate into a standard inspection, and your best bet is to recommend that they hire a professional to inspect for VGB compliance. And on a public pool in California, it has to be a licensed C53 contractor that inspects for VGB compliance. So if you don't have that license, you can inspect, but you can't write it up and the health department won't accept it.
Okay. And then what should we do? When should we do a field inspection versus when is it necessary or prudent to call in a pool expert such as yourself?
Well, the one thing you want to do is be real careful what you say about drains. I know it's been traditional for you guys for years to tell people to put in anti-vortex drain covers. And as I told you in the presentation, an anti-vortex drain cover does not mean a safety drain cover. It simply means anti-vortex, and then it only means anti-vortex if the flow rates are right, because I've certainly seen vortexes going around anti-vortex drain covers. And if you see single drains in pools, single drains in spas, you can immediately say you need to have somebody come out and look at these drains and do a professional evaluation of them. If you see dual drains, it's a good idea to do the same thing. This is a tricky area, and as you can tell from the presentation, it takes a lot of work to see if these pools are in compliance. So I think the best thing you can do in the field is outline what the problems are and quote Virginia Graham Baker, but don't go into the details of the law itself, and just indicate that you think or you feel that the drains are not in compliance and that this is an industry standard in residential pools, but not in public pools. It is a law in public pools. And at that time, you can recommend them to call in a pool expert.
Well, I think with this presentation, I know how to identify a compliant drain cover, but how do I know what the sump looks like underneath that drain?
Well, if you're in Southern California, which I know most of you are, you can assume that the sump is not there. I built 2,000 pools, and as I mentioned earlier, none of them had the proper sump. I've inspected God knows how many drains over the years, and I have yet to find a drain that has a proper sump under it. In other parts of the country, putting in a sump is almost automatic and it's almost always done properly, but in Southern California, Nevada, and a lot of places where the sumps are just built in the field, they're not going to be proper. So you can assume, and sometimes people won't believe you, but you can assume that the sump is not compliant. I typically will drain the spa into the pool, and I can do that, but I can't drain the pool into the spa, it won't fit. And then I remove the drain covers, and assuming that the screws aren't rusted, and expose the drain sumps and show them to the client. And of course they're never proper, and then I cover them back up after I take photographs for my records. So how do you know what they look like? They almost always just look like a shallow, very shallow sump, or no sump at all. The pipes, suction pipes, are almost directly under that drain cover lid.
Okay, thanks. What about vacuum fittings and any other submerged fittings?
Well, we have, as you know, equalizer pipes are often installed under skimmers, and we have vacuum fittings for pool cleaners that are on the side of the wall. A vacuum fitting for a pool cleaner should have a snap lock fitting, and you should test that fitting. And the way you test that fitting is by unplugging the vacuum and letting go, and it should snap shut. And that fitting, that cover, you should have to open that with a tool. Usually a screwdriver will do it, but it's not something you can open with your fingers. And it's certainly something you can't open once the pump is on. It should snap shut, and that vacuum should hold that lid shut tight. And the idea is that if somebody unplugs the roving pool cleaner, or even a standard pool vacuum, while the pump is on, that's going to snap shut, and the suction hazard will be non-existent. Equalizer pipes under skimmers. These pipes are put in, the only reason they're put in is to protect the pump. If the water level gets below the open throat of the skimmer, the pump will continue to work for another 20 minutes to a half hour until the water level gets down to the bottom of the skimmer. That's all these things provide. They are a suction hazard, and in my opinion, they're pretty much worthless. I've never known anybody to lose a pump or have a pump saved by one of these equalizer pipes. Now, I'm sure that in the vast world of swimming pools that there has been a pump or two saved because that equalizer pipe is there. But most pools today have automatic fill systems, and why put a hazard into a pool to protect a $700 pump? Doesn't make sense to me, but we do still see them in a lot of public pools. My recommendation is to abandon them. Simply plug them off. If you don't plaster over them, you should still have an approved drain cover over them, because while that eliminates the suction hazard, it doesn't eliminate the mechanical hazard. So you want to make sure that you still have an approved drain cover over them, so that you have the protection from somebody getting their finger stuck in the drain.
Okay. And then I understood the concept of measuring TDH, but where specifically do I get pump curve information for pools that I might be inspecting?
This comes with the manufacturer. If you go to any manufacturer's website and download their sell sheet, which is essentially their advertisement for the pump, or if you download the owner's manual, or if you download the installation manual, and often those are both one and the same. The pump curve will be in that information, in that document. That's the best source to get them. As I've told you, I keep a lot of pump brochures and owner's manuals on my website, so I actually have some pump curves for some obsolete pumps that are still out there and working. But the manufacturer is the source, and of course they develop these using approved testing conditions so that we know that they're accurate. Does that answer your question? Good luck getting that information. It's not that hard to find. It's not that hard to use. And if you measure TDH the way we talked about in the presentation, you'll be getting a much more accurate picture of the flow rate going through your pools.
Rick, I'd like to thank you very much for your time and your expertise today. We certainly appreciate you covering this VGB information for the home inspector audience, and thank you very much for your time.
Well, thanks a lot. I really enjoyed speaking to you guys today, and I hope it's all proved to be useful.